So I won't take too long because obviously there's a break after this and everyone wants some coffee. I'm going to talk to you about the behavior of nitrogen during magmatic differentiation. And so here's a photo of Earth's atmosphere. Almost every photo you take on Earth obviously has Earth's atmosphere in it, but it's translucent. This talk represents work I've been doing for almost over a decade, and I will continue to do until I die. There are no direct economic benefits of what I do. There are no direct societal benefits of what I do. There's overly ambitious quest to understand why is Earth habitable. And as the future looks bright for exoplanet science, we're soon to be getting information about the atmospheres around exoplanets, which is super exciting. But we still don't know why Earth's atmosphere is lovely. And the scientific term is habitable. So nitrogen's a good place to start. It makes up most of Earth's atmosphere. Back when I was a grad student, I was very much attracted to working on nitrogen. I was supposed to be working on carbon, but there was little known about nitrogen. So I thought, that looks fun. There are loads of questions. Everyone was working on carbon, so I decided to focus my life on nitrogen. Nitrogen's cycle itself is planetary in scale. So I've shown a sort of schematic here that just represents different reservoirs, right? You've got the classics: mantle, ocean crust, continental crust, atmosphere, hydrosphere. There are arrows going between all of these. There are feedback systems between them all. And so to understand nitrogen, if you break things down to the fundamentals, all elements must obey the laws of physics, right? And so we can quantify the nitrogen cycle to some degree if we focus on it. And specifically today, we're going to talk about partitioning behavior. So this is the preference of an atom to go from one place to another. An example being, if you have a basaltic melt and you're growing olivine, the nickel will jump into the olivine. However, if you have sulfides as well, the nickel is then compromised. It's like, oh, I like olivine, but I really like sulfide. And so people have spent ages doing experiments like the talk we just showed, looking at solubilities and partitioning behaviors. And we're going to focus now on, this talk is on the flux from when mantle melts, go into crust. Do they then go, what happens? You have a magma plumbing system, some sort of mush, mess, chaotic madness. Volcanoes release gas. Measuring the nitrogen flux at the top of a volcano is really hard because the atmosphere is like an infinite reservoir. So your background is infinity and you're measuring trace elements. So you might as well not bother. So how else do we get around this problem? When I was a postdoc in DC, I was doing some probe work and I was bored. So I productively procrastinated, which meant I downloaded the treatise in geochemistry and just started pissing around with plotting stuff. And one of the things I plotted was this, which is the nitrogen abundance of the atmospheres of Earth, Mars, and Venus. And I've normalized nitrogen to all the primordial noble gases. And this is because in terms of partitioning behavior, the noble gases don't like going in anything. They're not charged. They offer nothing to the crystal. They want nothing from the crystal. And 99.9% of these primordial noble gases are just floating around the air. The reason helium's so expensive is it's not gravitationally bound, which is why I haven't looked at it. So every time you breathe out helium and speak with a silly voice, it goes to space. So the cost of helium is insane. But I looked at this plot and thought, why is Earth got a relative enrichment of nitrogen relative to noble gases, in spite of the fact that, say, Venus has an atmosphere of 92 bars and 6 times more nitrogen? So something on Earth is fractionating nitrogen from the noble gases. And we found a way of calculating and made this horrific plot, which all we did is calculate the fluid speed. So this is an aqueous fluid in equilibrium with mantle rocks. And we found that for the majority of Earth's mantle, and the Venusian mantle and the Martian mantle, the conditions should be such that ammonium should be the stable nitrogen species in the fluid. And then here, in these more oxidizing conditions that we find in arcs, N2 should dominate. So then we thought, okay, that's great. We decided that arcs pumped nitrogen out of the mantle because N2 doesn't go into crystals. I've recently had a PhD student graduate, Dr. Formoso, I suppose I should call him now. He's now working in a superconductor manufacturing company. We ran some experiments and synthesized fluid-free glasses. So there's not always a free fluid, well, there probably is always a free fluid phase, but we wanted to know, do we find any ammonium in a silicate melt in an undersaturated conditions? And we ran some crude FO2 controls, but we did find that you can dissolve ammonium into a silicate melt structure. So that's sort of really exciting because it means that you've now got ammonium, which is similar in size and charge to large iron lithophiles and might partition like them, right? So this was the model that we published back in 2014, where we said arcs pump nitrogen out of Earth. Mars and Venus do not have arcs. This explains Earth's atmospheric chemistry. But in this cartoon, I just put that on Mars and Venus and on under Hawaii, say, and under mid-ocean ridges, you just have this ammonium that isn't lost. So where does it go? So you get a faculty job at some point, you sort of hire someone else who likes to build labs, and then you try and get a student. And you build a lab that enables you to make the measurements you need to do to answer the question, where does nitrogen go in igneous systems? And you hire a PhD student. This is Toby. This is Toby safely using a torch. He has burnt his hair off before a little bit. And so Toby built a gas line when he was an MSc geochemistry student at St Andrews, and it worked. We measured a whole bunch of samples. He got his name on a couple of more papers. As a consequence, the lab works and it's humming away. It's brilliant. Toby managed during COVID with almost no opportunities for fieldwork to email lots of people and get a huge sample collection, which he'll present this afternoon, which is why it's also super convenient that he's after me. I'm going to give you the nuts and bolts, and then he does the fun stuff with it. And his talk is this afternoon, and congrats to Toby. He submitted his thesis at 11 p.m. on Christmas Eve. And as I said, we published this analytical paper. This was Toby's first contribution to science, and that was his MSc. So we have the tools. Step 2, let's start playing with it, right? So we're going to use this tool now to look at very simple samples. So Paul Savage, when he was a PhD student, went with Julie Prutliak when she was a postdoc to Iceland, and they sampled this volcano, Hekla, and they looked for aferric samples that span basalt, andesite, dacite, rhyolite. Aferric just means when you look down a microscope, you can't see crystals. You zoom in enough, it's just quenching. So we assume whole rock equals melt composition. Not as good as a melt inclusion by a long shot, but not too bad to start. And at Hekla, the data look like nice crystal fractionation. You have basalt sort of looking like it evolves to rhyolite. The samples are aferric, so you don't have to worry about minerals affecting your data set in the melt composition. So this is the stuff that's thrown out of the plumbing system. When you plot the data generally, I actually use these now in second year petrology classes because Hekla is so boring. It looks textbook, looks fantastic. You plot up trace elements as well. Their incompatibles go the right way. The major elements show fractionation of ferromagnesium phases and feldspars. It's a really nice sample set. And we measured, basically, we said, right, and these samples have been studied to death. Every isotope system you can imagine, the trace elements, from oxygen, lithium, all the way through to thallium and silicon. So we were like, this is great. These samples are really well constrained. And Toby could only work in one lab during lockdown because he was only safety approved in one lab. So samples that were well constrained was great because all he had to do was go in the nitrogen lab he built and not burn himself to death. And we measured nitrogen in them, thinking that it was just going to be a case that they're either all going to be below detection or that as the melt evolves, the nitrogen is lost. And what we found is that nitrogen is strongly coupled to rubidium. I won't show all the data. And nitrogen-rubidium ratio doesn't change so much when you plot these samples against things like oxygen isotopes or lithium abundance. And so we said, wow, in this melt system, it looks like nitrogen's behaving like rubidium. But this would be true for ammonium or N2, because rubidium is just used as an incompatible element. If N2 was in this melt, it would be incompatible. The concentrations of nitrogen in these samples is below solubility. So there's no reason N2 would degas because you haven't got a concentration above the point that the melt can handle. So it's not a finished story. So we said nitrogen's not degassing below saturation. So maybe that implies it's charged, but that's a step too far. You can't really say that because you're still below the solubility of N2. But it was really cool to see that nitrogen wasn't lost, that fractionation increased the nitrogen content. So we said, okay, that sort of sets us up nicely to say, let's look at mineral-mineral partitioning now and try and get a handle on the speciation of nitrogen and maybe the size of ammonium, because ammonium's a charged ion, and so it doesn't like being on its own. The noble gases are like super happy on their own. Charged particles are like really insecure things that can't handle being on their own, and they just want to react and bond with something. And the bonding affects the size of the ammonium component in your new, more complex compound. So we're like, it's a pain. Anyhow, we think we have a solution to this. So Loch Doon is not only, it's a Pluton, zoned. It's not only convenient, we can drive there from St Andrews in the hire company gave me a low-riding Mercedes sports car, which is awesome on the motorway bit of the journey, but completely useless when you're driving around mud roads in Scotland in the weather that Toby and I experienced. So when you go on Google Images, Toby's like, Loch Doon. I Googled it. I was like, oh, it was lovely. Let's go spend the night in a pub. There was a pub quiz when we were there. We were like, this is going to be fantastic. It's going to be beautiful. It was horrible. Air shear, like wind and rain combined to make wind rain. That's when you can see the valleys, and you can see in this distance, you can see this material going this way, and then you look around and it's coming this way. And we were wearing waterproofs, but we were sodden throughout. I put my sunglasses on because my eyes were getting pelted by wind rain. And so we didn't get a full suite of the Loch Doon samples. Now, this shows you Loch Doon compared to the blue ones are boggy plains in Australia, which we're planning to analyse, but the green ones are Loch Doon. And we thought, great, let's get from gabbro to granite. This will be amazing. Wind rain meant that we cancelled after we just got enough samples to justify a thesis chapter in a paper. And we just couldn't handle it anymore. We bailed. I'm not a field person. Field people here are probably judging me right now. I don't care. It's horrible. And what we did is Toby painstakingly picked minerals, including separating orthoclase from plagioclase, which is a pain. And then we measured the nitrogen and the full geochemistry of these things as well. And I'm not showing you all the data. This is just the relative abundance of nitrogen in orthoclase and mica compared to the whole rock. And I plotted it against calcium because these are mostly like gabbroic to diuretic. So plotting against silicon means this is the narrowest range. They're granitic to diuretic. And what we found, which surprised us, was that orthoclase was soaking up all the nitrogen. At the start of the study, we said to Toby, measure whole rock, then measure biotite. If biotite equals whole rock, we just publish. But as you can see, biotite did not equal whole rock. It was significantly lower than the whole rock. And we were like, are these rocks just altered? So we did some checks. They were not heavily altered. Loss on ignition was low. Lithium abundances were not showing anything other than straight lines for fractional crystallization. And then we measured the orthoclase, which Toby was trying to get out of doing, obviously, because it was like picking orthoclase and plagioclase apart with tweezers sucks. But he did it, and it's totally worthwhile. So we found that orthoclase was the dominant host of nitrogen in this particular system. And so we compared that, say, to rubidium. So now this is just the nitrogen content versus the rubidium abundance in whole rock and biotite and orthoclase. And actually, so initially with this data set, right, you'd say these are two potassic phases, right? They both contain potassium. Ammonium behaves like a large iron lithophile. So you'd say, okay, nitrogen's behaving like a large iron lithophile, but it isn't going into biotite as much as it is the orthoclase. So it has some preference for orthoclase over biotite. And when we look at rubidium is more compatible in biotite than orthoclase. So saying nitrogen behaves like a large iron lithophile isn't true. It's not accurate. It's behaving like potassium, not rubidium. So we don't presently know if this is because rubidium's competes. There's an exchange equilibrium going on. Rubidium's happier in biotite. Maybe between those sheets, the size is bigger, and rubidium's a big atom. And ammonium is actually smaller than rubidium and fits better in orthoclase, which is a much more rigid crystal structure. And so fitting a bigger atom in is harder. It's quite literally like kids' toys, fitting shapes in, right? So this is an open question that we aim to explore. And so we think that ammonium is the stable phase of nitrogen in the system, in the silicate melt system, or potentially in a fluid in this sort of mush madness, because this is still a Pluton, it's chaotic. But there does appear to be equilibrium behavior, and I won't show today for the sake of continuity and clarity. If anyone's interested in the isotope data we have some phenomenal isotope data where there's equilibrium isotope fractionation occurring between the biotite, the orthoclase, the plagioclase, and the whole rock. And so what we think is happening now, when we started Toby's PhD, the assumptions were that when nitrogen is present in a magma chamber and there's a volcano above the magma plumbing system, and it's degassing, that most of the nitrogen will be going into the atmosphere, and a tiny amount will be stored in the crust. After Toby's thesis, we now think that a significant flux of nitrogen, as long as you're below saturation, will be stored in plutons as they crystallize with K-bearing phases. And therefore, the flux of nitrogen into Earth's crust has been massively underestimated, and the flux of nitrogen into Earth's atmosphere is massively overestimated. And this just explodes a plethora of questions and variables that we need to constrain, and we hope to. We have PhD projects advertised and writing grants to move this forward. And with that, I'll say thank you very much, and I'm done.